this is an equation where we're trying to solve for a function f that depends actually on 4 variables, x, y, z, and t. And what should you think of, what should you have in mind? Well, this equation governs temperature. So if you think that f of x, y, z, t will be the temperature at a point in space at position x, y, z, and at time t, then this tells you how temperature changes over time. It tells you that at any given point, the rate of change of temperature over time is given by this complicated expression in the partial derivatives in terms of the space coordinates x, y, z. So if you know, for example, the initial distribution of temperature in this room, and if you assume that nothing is generating heat or taking heat away, so if you don't have any air conditioning or heating going on, then it will tell you how the temperature will change over time and eventually stabilize to some final value. Yes? Why do we take the partial derivative twice? Well, that's a question, I'd say it's a question for a physics person, but actually I'm going to, no. In a few weeks, we'll actually see a derivation of where this equation comes from and try to justify it. But really, that's something you will see in a physics class, okay? The reason for that is basically physics of how heat is transported between, particles in a fluid, or actually in any medium. But this constant K actually is called the heat conductivity. It tells you how well the heat flows through the material that you're looking at. So anyway, I'm giving it to you just to show you an example of a real-life problem where, in fact, you have to solve one of these things. So now, how to solve partial differential equations is not a topic for this class. It's not even a topic for 1803, which is called differential equations without partial, which means there actually you will learn tools to study and solve these equations, but when there's only one variable involved. And you'll see it's already quite hard. And if you want more, then later on we have many fine classes about partial differential equations. But, one thing at a time. So just I wanted to point out to you that very often functions that you see in real life satisfy many nice relations between their partial derivatives. Okay, so that was, in case you were wondering why on the syllabus for today it said partial differential equations. Now we've officially covered the topic. That's basically all we need to know about it, okay? But we'll get back to that a bit later. You'll see. Okay. If there's no further questions, let me continue and go back to my list of topics. Oh, sorry, I should have written down. Okay. That this equation is solved by temperature at the point x, y, z at time t. Okay. And there are actually many other interesting partial differential equations. You will maybe sometime learn about the wave equation that governs how waves propagate in space, about the diffusion equation, which tells you how, when you have maybe a mixture of two fluids, how they somehow mix over time, and so on. There's basically, to every problem you might want to consider, there's a partial differential equation to solve. Okay, anyway, sorry, back to my list of topics. So one important application we've seen of partial derivatives is to try to optimize things, try to solve minimum maximum problems. So remember that we've introduced the notion of critical points of a function. So a critical point is when all the partial derivatives are 0. And then there are various kinds of critical points. There are maxima, there's minima, but there's also saddle points. And we've seen a method using second derivatives to decide which kind of critical point we have. So I should say that's for a function of two variables to try to decide whether a given critical point is a minimum, a maximum, or a saddle point. And we've also seen that actually that's not enough to find the minimum or the maximum of a function, because the minimum or the maximum could occur on the boundary. So just to give you a small reminder, when you have a function of one variable, if you're trying to find the minimum and the maximum of, say, a function whose graph looks like this, well, you're going to tell me quite obviously that the maximum is this point up here, and that's a point where the first derivative is 0. That's a critical point. And we use the second derivative to see that this critical point is a local maximum. But then, when we're looking for the minimum of the function, well, it's not at a critical point. It's actually here at the boundary of the domain of, the range of values that we're going to consider. So here, the minimum is at the boundary, and the maximum is at a critical point. So similarly, when you have a function of several variables, say of two variables, for example, then the minimum and the maximum will be achieved either at a critical point, and then we can use these methods to find where they are, or somewhere on the boundary of the set of values that are allowed. So it could be that, we actually achieve a minimum by making x and y as small as possible, maybe letting them go to 0 if they had to be positive, or maybe by making them go to infinity. So we have to keep our minds open and look at various possibilities. So we're going to do a problem like that. We're going to go over the practice problem from the practice test to clarify this. So another important cultural application of minimum maximum problems in two variables that we've seen in class is the least squares method to find the best fit line or the best fit anything really to find, when you have a set of data points, what's the best linear approximation through these data points.